6 months ago, I reinforced the column of my milling machine with epoxy concrete. The result was a more rigid machine that also resonated less quickly. But all in all, the result was not really fantastic, with 40% less deflection than before. I received a lot of responses, and just like the impression I had from several epoxy pouring YouTubers, most of it was guesswork. Because I still had some epoxy left and gravel and sand cost almost nothing, I had been planning to do an epoxy concrete strength test for a while. In this video, the report of this epoxy torture. Here, I measure out 4 fillings, one of quite large pebbles, one of small pebbles, one of very fine sand, and one of a mixture of large pebbles and sand filling the gaps between the pebbles. I use water to determine the empty space between the stone, so that I know exactly how much epoxy resin I need per filling. When you think about it a bit, you quickly come to the conclusion that a mixture of finer and coarser material provides the highest filling degree. And that means that the least amount of fairly expensive epoxy is required. And since pebbles are always more dimensionally stable than epoxy, you would be inclined to think that such a mix offers the best solution. On the other hand, the finer the fill, the greater the common surface area, and lots of surface area for the epoxy to adhere to is probably better. As for the costs for the epoxy, it is clear. I measured almost 50% space between the larger pebbles, so almost half the volume of the concrete is epoxy. For the fine sand, it is roughly a third, and the winner with only 18% epoxy is the mixture of coarse and fine. But with over 18,000 square centimeters of surface area, the fine sand has more than twice as much surface area as the mixture of sand and pebbles, and no less than 28 times the surface area of the coarse pebbles. I make 4 tubes here from self-adhesive aluminum foil. I leave the plastic foil on the inside, in the hope that I can easily peel the aluminum off the cured rods later. Except for the mix of coarse and fine, mixing is very easy and air bubbles rise quickly through the very slow-setting thin liquid epoxy. The sand between the coarser pebbles makes thorough mixing much more difficult, and I am also less confident that I am not leaving any air bubbles trapped in the rod, as I am left with some pebbles. Fortunately, the foil on the inside provided the desired results, and the outer layer was easy to peel off the epoxy rods, which are known to adhere very tightly to almost anything. And after 48 hours of curing, the test rods are ready. A steel rod will serve as an aid in measuring the deflections and analyzing any measurement errors. Even though I have taken great care of it, the rod with the mixture of coarse gravel and fine sand still contains some air bubbles. With some crazy glue, I attached 2 blocks of aluminum to the granite table, and with some aluminum and steel, I make a simple test instrument. A 2-kilo lead ball and considerable leverage provide a force of 225 newtons on the middle of the bars to be tested. Here I switch to a more sensitive indicator. The rods are not perfectly round, and especially with the rod containing the large pebbles, the homogeneity could be better. To eliminate the consequences of this in the measurements as best as possible, I measure each rod 6 times, rotating it 60 degrees each time. The average deflection is recorded in the measurement results, and the maximum difference between the measurements is a measure of homogeneity. I am not at all satisfied with the measurement results. They vary too much and are poorly reproducible. There must be something wrong with the measurement setup. And after some thinking, I came to the conclusion that here I am, not only measuring the deflection of the rod, but also the deformability of the surface of the test rod. If the steel lever accidentally presses on a pebble, there is little deformation, but when the force is applied to the much more flexible epoxy, it is easily depressed by a few microns. The surface area that absorbs this pressure must therefore be much larger to eliminate these differences. This setup gave much better results. Not only is the force now transferred through a large surface area, but I have also switched to applying a preload of 200 newtons, but still the results were not really clear. This was particularly visible with the steel test rod. This is an accurately round and true tube, yet the deflection measurement results varied by as much as 5 microns. I think this is the culprit. I glued a block of steel with a concave bottom to the tension belt on which the indicator probe rests. But that belt can deform somewhat under varying loads, and that deformation is included in the measurement results. Particularly if the surface of a rod is not perfectly round, the resulting deformation can add up to several microns. Essentially, by placing the indicator tip on top, I made the same kind of mistake twice. By placing the small steel measuring surface directly on the test rod, I eliminate these types of measurement errors. The fact that the measuring surface is not exactly in the center of the rod is not a problem. The formula with which the final resistance to deflection is calculated can easily be adjusted for this. That looks much better. The differences between the 6 measurements of the steel rod are now limited to 1 micron, and the results are highly reproducible. Of course, the Young's modulus, which is the resistance to deformation, of steel is well known. Considering the force exerted, it can be calculated that this rod should bend slightly more than 2.5 microns. The measurements give a result of 8 microns. The difference of approximately 5.5 microns must lie in the deformability of the 2 aluminum supports and the deformation of the granite tabletop. Because I use exactly the same setup and forces for every measurement, it is reasonable to correct the measurements of the epoxy rods for this. Here I ensure that the band is positioned as best as possible in the center of the test rod every time. This is essential because the measurement results depend on the cube of the length. The deflection under longer-term loads has also been tested. After 10 seconds, very fine is the best, with 24 microns of deflection. Fine and the mixture are equal to 32 microns, and the rod with the coarse pebbles is clearly the worst in deflection at 68 microns. After 2 minutes, very fine is still in the lead at 35 microns, but closely followed by fine at 38 microns. The mix has bent further to 48, and the coarse epoxy concrete has dropped all the way to 110 microns. This graph gives a clear impression of the resistance to bending of the test bars and how homogeneous the epoxy concrete mixture is. The red line is of the coarse pebbles. This is clearly the least desirable filling, not very homogeneous, and the weakest of all four. The somewhat stronger filling of fine pebbles is also certainly not optimal, as the green line shows. The best result is given by the mixture with the fine sand according to the purple line. This is the most homogeneous and strongest epoxy concrete. The mix of pebbles and sand is even stronger in some places, but is very inhomogeneous. All in all, I draw the following conclusions. If dimensional stability and strength are not of great importance, and costs must be kept as low as possible, choose a mixture of pebbles and sand. Only 18 volume% epoxy needs to be used for this. However, the high risk of trapping air bubbles must be taken into account. A vibrating table or vacuuming for a short time to allow the air bubbles to rise can also offer a solution. But if dimensional stability, homogeneity, and reliability are a prerequisite, then it is better to opt for double the epoxy price of the excellently castable mixture of fine sand and epoxy resin. And in any case, choose an epoxy that hardens as slowly as possible, so that any air bubbles have time to rise. Also, never make uneven and unreliable mixtures of stones, huge pebbles, sand, and other materials, as I saw on some YouTube videos. And when it comes to increasing the rigidity of a machine, keep your expectations in check. It might help if you do it right. In some cases, adding reinforcement to the concrete could also be beneficial. That's it for this time. I hope to see you again.